Hey everybody. Today we're talking about the expected value of discrete random variables. This is just a weighted average of all the values that random variable can take. A bit more mathematically, the expected value, written E of x, is the sum of x times f of x, where x is the random variable, f of x is the probability mass function, and the summation is done over all the possible values that the random variable can take. In other words, we're adding up over the support of the random variable. The expected value is also called the mean of the random variable, denoted mu or mu sub x. Here's an example. It's not a bad idea to try this before advancing. I have a random variable here with 5 possible values and their respective probabilities. To get the expected value, I'm going to take each of those values, multiply by its respective probability. So for instance, 60 times 0.22, 70 times 0.14, etc. I multiply, I add all those up, I get 77.8. If we were to draw many values from this distribution and take their average, we would expect to get 77.8. Expected value measures the center of a probability distribution in much the same way as the mean does for a data set. So if you make a discrete probability histogram like the one that we're seeing here, the expected value is the balancing point of that histogram. More generally, we can find the expected value of a function of a random variable in kind of the obvious way. You take all of the values that that function of the random variable can take, so basically just adding up over the support of the random variable. You weight each one by its respective probability. Related example to the one we had a second ago, taking that same probability distribution, finding the expected value of the square root of x. So, in this case, I'm going to take the square root of 60, 70, 80, 90, and 100, weight each one of those by their respective probabilities, so doing things like root 60 times 0.22, root 70 times 0.14, and so on, multiplying, adding everything up, I get about 8.79. Now, one warning as we're talking about functions of random variables. It's almost never the case that the expected value of a function of a random variable is the same as the function of the expected value. For instance, in that last example, the expected value of the square root of x was 8.79 approximately. But the square root of the expected value of x, the square root of 77.8, is about 8.82. So you really need to resist the temptation to swap the order of operations when you're doing expected values of functions. Mathematical expectation does have some other convenient properties, though. If you have a constant c, a random variable x, and two functions, u and v, the expected value of c is c, so the expected value of a constant is just the constant. That makes sense. The expected value of a constant times a random variable or times a function of a random variable can be done just by factoring out the constant. It doesn't matter if the constant multiplication is done inside or out. By the way, that only works for a constant. As our general rule, it doesn't work if instead of c we have another random variable y. Finally, the expectation of a sum is the sum of the expectations. The last 2 bullet points here are summarized by saying that expectation is a linear operator. Proofs involving expected value almost always start out with a definition. For instance, if we were going to prove the third of those bullet points, we would simply write the expected value of u of x plus v of x using that definition. The sum over all the elements x in the support of u of x plus v of x times f of x. Distributing out the thing in brackets in the upper right there, breaking up the sum into 2 pieces, we get 2 different expected values, proving the fact that we had on that last slide. Not all random variables have a well-defined expected value. For instance, suppose we have a random variable x with probability mass function 6 over pi squared times s squared and support of all the positive integers. This is a legitimate probability mass function since the sum of 1 over k squared from k equals 1 to infinity is pi squared over 6. And that's a good sort of calculus 2 exercise. The random variable x here does not have an expected value, however. If we do the sum of x times f of x, factor out the constant 6 over pi squared, we end up doing the sum of 1 over x from k equals 1 to infinity. That's the harmonic series, which we know does not converge. So in this case, we have a legitimate random variable with support going from 1 all the way up to infinity without an expected value.